Type 1 and Type 2 errors. Understanding what can go wrong in hypothesis testing. When we make a decision in hypothesis testing, there are two kinds of mistakes we can make. The first is like convicting an innocent person. We reject H0 when it's actually true. This is a Type 1 error, also called a false positive. The second is like letting a guilty person go free. We fail to reject H0 when it's actually false. This is a Type 2 error, a false negative. Both mistakes have real consequences, and we need to understand how to balance them. Let's organize this in a decision table. The columns represent reality, whether H0 is actually true or false. The rows represent our decision, retain or reject H0. When H0 is true and we retain it, that's a correct decision. When H0 is false but we retain it, that's a Type 2 error with probability beta. We missed a real effect. When H0 is true but we reject it, that's a Type 1 error with probability alpha, a false alarm. And when H0 is false and we correctly reject it, that's the power of the test, 1 minus beta. Alpha is the probability of a Type 1 error, rejecting H0 when it's actually true. This is set by the researcher, typically at 0.05 or 0.01. Beta is the probability of a Type 2 error, failing to reject H0 when it's actually false. Beta depends on the true effect size and the sample size. Power equals 1 minus beta. It's the probability of correctly rejecting a false null hypothesis. In other words, power is the ability to detect a real effect when one exists. Let's visualize these concepts with overlapping distributions. The green curve on the left represents the sampling distribution if H0 is true, with mu equals 170. The purple curve on the right is the distribution if the alternative is true, with mu equals 190. The dashed line marks the critical value. If our sample mean exceeds this value, we reject H0. The red shaded area in the right tail of the green curve is alpha, the probability of a Type 1 error, rejecting H0 when it's true. The orange area under the purple curve to the left of the critical value is beta, the Type 2 error, missing a real effect. And the yellow region, the right portion of the purple curve beyond the critical value, is the power, the probability of correctly detecting the effect. How do we increase power? The most direct way is to increase the sample size. With a larger n, the standard error shrinks, making both distributions narrower. Here we've gone from n equals 64 with SE of 5 to n equals 144 with SE of only 3.33. Look at how much larger the power region becomes. The distributions are much more separated, making it much easier to detect a real difference. This is why sample size planning is so important in research design. There's an inherent trade-off between these errors. If you make alpha stricter, like going from 0.05 to 0.01, beta increases and you lose power. It's harder to detect real effects. The best way to improve things is to increase the sample size, which reduces both types of errors. Also, larger effect sizes are easier to detect, naturally reducing beta. The standard practice is to set alpha at 0.05, then calculate the sample size needed to achieve adequate power, typically 80% or more. To summarize, a Type 1 error alpha is rejecting a true null hypothesis, a false positive. A Type 2 error beta is retaining a false null hypothesis, a false negative. Power equals 1 minus beta and represents our ability to detect real effects. The best way to increase power and reduce errors is to increase the sample size. These concepts are essential for designing reliable studies.